Hi, my name is Anthony Spradling, and this is my Lab 1 submission about constant velocity. In this lab, the objective is to observe the motion of an object with no forces acting upon it during a short time interval through video. The goal was to compare observed position over time in the real world, where conditions are imperfect, to a computational model with the same force and velocity conditions to find the predicted position over time. Some of the models used in this experiment were position versus time graphs, where the slope of the line is the velocity, glow script computations to derive expected values, and tracker computations to measure physical values from a video recording. Some of the important physical principles in this lab were position, velocity, forces, the velocity update formula, and Newton's laws. By the end of the experiment, we found that the computational model showed a slight deviation in position from the observed model, but it seemed to be a good estimate for the position of the object during the short time interval used. The main physics ideas of the lab are that during the short time interval chosen, the velocity of the marker used in the experiment was relatively constant. This is because during the interval, the forces acting upon the object, like friction that would slow it down, didn't have enough time to make a significant effect on the object. If we look at the velocity update formula pictured here, we can see that the time interval t, which we defined to be 0.13 seconds in this experiment, the velocity of the marker in the x direction is dependent on the forces being applied to it in the x direction. The equation comes from Newton's first law, describing that an object in motion will stay in motion unless acted upon by an external force. As we detailed earlier, we're going to assume that there are no external forces in the x direction, since we have chosen such a small time interval. If we plug in these values for the velocity update formula, we see that no matter what the time interval is, the final velocity of the object will equal the initial velocity when there are no forces. What we need now is to find the average velocity during the time interval. To do this, we will use the equation v average equals the change in position over the change in time. In the tracker model presented here, we can see that the marker is the object we are comparing over time. We define the marker as a system, and everything outside of the marker, like the table, etc., as the surroundings. The initial conditions for the object are its initial velocity, which we will calculate in the next step, and its initial x position, which we define to be 0.01296 meters. In tracker, we use the point mass to determine the position of the object over the time interval starting at time 0 until time was 0.013. These were the same initial conditions given to the computational model. Here we are finding the average velocity of the marker during the time interval, 0 to 0.13 seconds. In the tracker model, we found the final position and initial position for these quantities, and we plugged them into the velocity average formula from earlier to get an average velocity of 0.27372 meters per second. Now in the glow script model, we can see that we have defined our initial position, velocity, and force vectors with the starred marks. We input the values we found as initial in the tracker model and let the computation run to see where the expected position would be in the end. This computational model works by using the position update and velocity update formulas and iterating these equations over short time intervals to find new positions and new velocities. These formulas are marked with stars here. In the program, we have set it to run iteratively every 0.01 seconds and to go from 0 until 0.133 seconds, which is a final time of the marker in the tracker data. In this slide, we compare the glow script data to the tracker data and see that over such a short time interval, the data seems to align quite well. The tracker data highlighted in blue on the graph seems to not be linear like we expected it to when there are no forces. We know that in reality, these net forces like friction are there, which will account for some of these errors. Another source of error could also come from the camera because it's incapable of viewing the surface as fully horizontal because of the angle the camera is coming from. This causes us to get slightly inaccurate position vectors from the tracker. What would also be helpful is if we were able to get more data points from the tracker, but they only allowed us to move in certain time steps, and we wanted to keep the time interval short so the external forces like friction wouldn't have as much effect on the position and velocity of the marker. In the end, we determined that at 0.13 seconds, the computational model of the marker had the position slightly further than the tracker model. If we were to flip the axis of the model, the result would largely remain unchanged. If we were to say the marker was going in the negative x direction, all that would change is that the velocity would now be a negative number of the same magnitude as before. As for the position, it would also just be a negative number of the same magnitude as before in both the computational and tracker models. To the question, would it be possible to see how many forces are being added together to give a net force, that the answer is not really. If we know what all the forces are that are creating the net force, then yes. But in this case, we would need more information to determine the forces of friction and wind resistance, rotational inertia, and some other things. Thank you.